This video is going to talk about cyclic quadrilateral. It's going to be talking about the different properties of a cyclic quadrilateral. Things like opposite angles of a cyclic quadrilaterals are supplementary. It will be talking about exterior angles is equals to opposite interior angles of a cyclic quadrilateral. We'll also be talking about shapes that do not look like a cyclic quadrilateral, but they are a quadrilateral, then we need to prove that they are cyclic. These are some of the things we're going to talk about today. A quadrilateral is a four-sided shape, while a cyclic quadrilateral means that you have a circle and each of the vertex of this four-sided shape is on the circumference of that circle. Now, when you have your cyclic quadrilateral, there are two major properties of a cyclic quadrilateral. The first one is opposite angles of a cyclic quadrilateral are supplementary, meaning that they add up to 180. And the second property of a cyclic quadrilateral is exterior angles is equals to the opposite interior angle of that cyclic quad. Now, the theorem in which we use in cyclic quadrilateral is opposite angles of a cyclic quadrilaterals are supplementary. We are going to go over the proof right now. Now, this proof is trying to confirm the statement the opposite angles of a cyclic quadrilaterals are supplementary. Supplementary, as we said before, means that they add up to 180. To prove this, we have to understand that the center of the circle is O, which we have over here. We also have A, B, C, D on your circumference. They are vertices on your circumference. We are required to prove that DAB, that angle over there, plus DCB, this angle over here, add up to 180. We could also prove that ABC plus ADB add up to 180. Now, we don't have to prove both of them at the same time. We just need to prove one of them, and if this is right, the second one would also be right. So now, to prove this, the first thing we need to do, as we do for every proof, is to construct something to help us draw this. So we're going to connect a line from D to O and from B to O. The second thing we're going to do is we're going to label. Let's call this X. Let's call this Y. The top part of our O, let's call that 1. The bottom part, let's call that 2. So all we did is that we said DAB is equals to X and DCB is equals to Y. Then we have that DOB as 1 on the top part, and the bottom part we call that 2. Let's get into proving. So from the second theorem, we understand that O2 would be equals to 2x, because that angle is double. Angle at center is equals to twice angle at circumference. And because of that, we also understand that O1 would be equals to 2y. Same reason. We also notice that O1 and O2 makes up angles around the point. So we actually understand that O1 plus O2 would be 360 angles around the point. Then therefore, so we're replacing the O1 with 2y and the O2 with 2x. Then we can chain them back, which becomes, then we divide everything by 2. Now, if this works for one side of our quadrilateral, it has to work for the other side. We know that ABC plus ADB would also be 180 degrees. And that's it. So this is exactly how you prove opposite angles of a cyclic quadrilaterals are supplementary, meaning that they add up to 180. And that's the proof. Now let us do an example using this proof to answer questions involving opposite angles of a cyclic quadrilaterals are supplementary. Now this question wants us to find A, wants us to find B, and wants us to find C. We're going to use the concept of opposite angles of cyclic quadrilateral to help us get our answers. But first of all, before we get to that, let's start with A. To calculate our value for A, We understand since POQ is a diameter, why we know is a diameter is because it passes through O, which is the center of your circle over here. A would be 90 degrees. To calculate B, since PSQ is a triangle, we can use sum of angles in a triangle to help us calculate B. And finally, to find C, we can see that P and R are facing themselves. So since they're opposite facing angles, and this is a cyclic quadrilateral because it touches P, it touches Q, it touches S, and it touches R, all your vertices are on your circumference. We understand that to get that, we just need to use opposite angles of a cyclic quadrilateral as a supplementary. That's it. So let us talk about a four-sided shape, a quadrilateral, in which there is no circle for us to know that it's a cyclic quad. Now, how do we prove that something is a cyclic quad? We have three ways of proving it. We either prove that the opposite sides add up to 180. So we are saying something like, if we can prove that A plus C is equals to 180, or we can prove that B plus D is equals to 180, then it's definitely cyclic. And the reason that we'll give for this statement is opposite interior angles are supplementary. We prove the exterior angles is equals to the opposite interior angles. The other way we can prove a quadrilateral is cyclic is if we can prove that A is equals to the angle outside of C, meaning that A is equals to DCE. We can give the reason to be exterior angle is equals to interior opposite angle. We also prove that angles in the same segment forms on each of the vertex of this quadrilateral. We can prove that A is equals to C and B is equals to D. Angles in the same segment are equal. That's another way we prove quadrilaterals are cyclic. We can't say that these quadrilaterals are cyclic without using one of these three proofs. That is exactly how you prove quadrilaterals are cyclic. Now, there's one thing that is very important. Until you prove that the quadrilateral is a cyclic quad, you cannot use any of the properties. Let us do an example to put some of this into perspective. So we have this shape over here. We have O being the center of the circle in this shape. We have angle at E is 90 degrees. And we're asked to prove that ABDE is a cyclic quad. So the goal is to prove that ABDE is a cyclic quad. E is 90 degrees. And we know that because it was given in the question. Now we also see that we have a diameter. And normally whenever we have a diameter and it subtends an angle, that angle would be 90 degrees. So that is angles in a semicircle. DBC is 90. Now since E is 90 and DBC is also 90, E would be equals to DBC. And therefore ABDE is a cyclic quad. And the reason is a cyclic quad, exterior angle of a cyclic quad is equals to the interior opposite angle. So since that is 90 and this is the exterior angle and is equals to the opposite interior angle that we have here, this whole shape would definitely be a cyclic quad. And that is how you show a quadrilateral is a cyclic quadrilateral. In the next video, we'll be talking about another question on proving a quadrilateral is cyclic. This is what you need to know to be able to understand cyclic quadrilaterals. Please do like and subscribe. Thank you.